In this lecture segment, we're going to talk about polyprotic acids and base chemical equilibria. Now, in the last lecture, we talked about monoprotic acids, and as the word suggests, mono means only one ionizable proton, is being dissociated. With polyprotic acids, you've got more than one ionizable hydrogen. For diprotics, you've got 2. For triprotics, you've got 3, and so on. Now, there are many examples of polyprotic acids and bases, in the environment and in nature. For example, you're going to find, most of the amino acids, the 23 amino acids, that make up different types of peptides and proteins. All of them, you're going to find they've got an amino group, which can be protonated, meaning is an acid. But they also have, the carboxylic acid group, okay? And so in that case then, is at least a diprotic acid. A good example is glycine, and glycine is the smallest sort of molecular weight amino acid that makes up different types of proteins. And you can see that it's got, a hydrolyzable proton, but also, if it's protonated in this form, then it's a diprotic acid. You can lose one hydronium ion, and the pKa1 is as such. 2.35, and also you can lose an hydrogen from the protonated amine group, and the pKa2 is equals to around 9.78 to get the fully deprotonated base. But other than amino acids, you also have other types of polyprotic acids. A good example is sulfuric acid, amino acid, and it's got 2 hydrolyzable protons. Also a good example is vinegar, acetic acid. Again, it's got 2 hydrolyzable hydrogens. Got something like oxalic acid, another very common type of diprotic acid. If you get a bee's or a wasp's sting, often, you get that sting, that feeling of a sting because of the oxalic acid, that is emitted by different types of ants. And again, it's got 2 protonatable, hydrogens. And so there are many different types of polyprotic, acids and bases, in nature. And like I've said, amino acids are classical examples. So let me use an amino acid, glycine, as an example, to take you through the different ways you treat a polyprotic acid-base equilibria system. Now, you've got glycine. You got glycine right there, as I've said. It's got 2 hydrolyzable, protons, meaning it can undergo one hydrolysis, to give you an ampiprotic species, plus a hydronium ion. Now, these ampiprotic species can further undergo hydrolysis, the Ka2, to give you, the deprotonated base, and an hydronium ion. And of course, you can set up, the equilibrium expression as follows, the products, concentrations, divided by the reactant. And similarly, you can do the same, for the second hydrolysis, or rather dissociation reaction. But remember, each one of these, the bases here can further undergo hydrolysis. For example, the deprotonated base, can react with water, capture a hydrogen, and that way you get the ampiprotic species, the Hg, and then you get, the OH, and that's what you call the Kb, the Kb1 in this case. So it's a hydrolysis, type of reaction. And the corresponding, hydrolysis expression is as such, the products divided, of course, by the reactant. This Hg again can undergo further hydrolysis, the Kb2, to give you back the fully protonated glycine and a hydroxide, and the corresponding, equilibrium expression, is as such. And so you're gonna find if you take reaction 1 and combine it with reaction 2, you can find, these guys cancels out, and what you're gonna be left actually with, it's water, giving you the hydronium ion and the hydroxide, and so that gives you essentially the Kw. So if you combine reaction 1 and 2, you get this kind of expression, the autoprotolysis, constant. The Kw is equals to the Ka1, multiplied, by the Kb2. On the other hand, if you combine these two reactions, as you can see, the Hg cancels out, the G minus cancels out, and so what you have left, it's water giving you H plus, and OH minus, and again you get this kind of expression, autoprotolysis, constant, where the Kw is equals to, the Ka2 multiplied by the Kb1, the Kb1. So hopefully that's very clear, okay? So the Kw is equals to the Ka1 multiplied by the Kb2, and that is of course the base constant, the base constant, the Kb2, and so forth. And of course there are many different types of acids, amino acids, 23 of them. Most often, they are diprotic acids such as alanine. You can see it's got a pKa1 and the pKa2. Okay, and of course that is the carboxylic acid, that is giving up the hydronium ion, and then the ammonium, is a much weaker acid, and that's why it's Ka2, is fairly small. But you also have some amino acids, which have got up to 3 hydrolyzable, protons, and in that case, they are triprotic acids, something like this, they are triprotic acids, something like arginine, you can see is a triprotic acid. Something like aspartic acid, again you can see is a triprotic acid. Something like histidine, it's an aromatic, type of an amino acid, very common, again you can see, it's got a Ka1, a Ka2, and a Ka3, meaning it's a triprotic acid, and so forth. And the other amino acids, like tryptophan, again you can see it's a very common type of amino acid, present in milk. And you can see again the Ka1, which involves the carboxylic acid, dissociating, is the strongest of the functional group, that is acidic, is 2.4, and then the ammonium group, again it's an acid, it gives you 9.3, and that's a pKa2. So again you can see it's a diprotic acid. Tyrosine, on the other hand, and tyrosine really it's what gives it's a building block, of melanin, the pigmentation on the skin, and you can see that one it's got, is a triprotic acid, meaning it's got 3 hydrolyzable protons. So you can see the importance of polyprotic acids as building blocks, of peptides, as building blocks of proteins. And of course, proteins is what really makes up, tissues and life in general. So in this lecture, what I'd like you really to focus on, or I'd like us to focus on, is how do you calculate the pH of polyprotic acids and bases. Now, I'll give you an example. Assume you've got a diprotic acid, such as glycine hydrogen chloride, which is here, and I make a solution of 0.05 glycine hydrogen chloride. As you can see, the chloride dissociates completely, so it's not very important in this case, and what we are left with, is a glycine, which is a dihydrogen glycine, meaning it's got two hydrolyzable, protons. How do I get the pH, from this solution of, 0.05 molar, 0.05 molar of H2G, which is the glycine, okay? Now, the way you do it is, of course, there are many reactions taking place, one of which is, the H2G plus, of course, we know is going to hydrolyze Ka1, to Hg, plus the H plus, the hydronium ion. But I also know whatever I form here, can hydrolyze further the Ka2 to give me the G2 minus plus, the hydronium ion. So I've got those two equilibrium expressions here that are gonna result, out of the glycine hydrolyzing. Take note of this. If you look at the magnitude of the Ka1, it means that this reaction it's much more prevalent, than the second reaction, because you can see the second reaction is about 7 orders of magnitude less compared, to this. So in fact, when you're calculating the pH, you can essentially neglect, the effect, of the second dissociation and simply treat, these diprotic acids simply as a monoprotic acid. I hope that's clear. Okay, meaning is a regular monoprotic acid, meaning is a predominantly, only the first reaction is taking place. Now, of course, we know, for monoprotic acids, I get it hydrolyzing as follows, it's a 1-to-1 stoichiometry, meaning I get X forming for the hydronium ion and X forming, for the ampiprotic species. And so the Ka1 really is equals to what we have here, which is the X multiplied by the X, because it's a 1-to-1 stoichiometry, divided by the formal concentration, minus X, which is what I have here. Now, in most cases, you don't really need to solve a quadratic equation, because you make an assumption. You make an assumption that F minus X really is equals to F, and F refers to the formal concentration, which is equals to 0.0500 molar concentration. Okay, but of course we are making this assumption by saying that the 5% rule, or the percent dissociation, is not that significant. Okay, and what you get here is a pH of 1.889. Okay, if the 5% rule doesn't hold true, and in this case I'm confident it will not hold true, then you have to solve the quadratic equation, which is again fairly straightforward using the quadratic formula, which is shown here. I hope it's clearly clear. So that is if you're calculating the concentration of A, which is 0.05 molar of glycine hydrochloride. That's what I made in the lab, and I wanted to get the pH of that solution. So again, I treat it, like a simple monoprotic acid dissociation, because I'm neglecting, the second dissociation, because you can see the Ka2 is very, very small compared to the Ka1. Now, what if on the other hand, I had the monohydrogen glycine, that I got from the shell when I made this solution? What would be the pH in that case? Now, remember, this is an ampiprotic species, meaning it can undergo dissociation, so it can behave as an acid, and you can see this is the Ka2, but also it can undergo hydrolysis, meaning this is the Kb2, meaning it can undergo hydrolysis. Okay. Now we already know that is an amphiprotic species. If at all you've been given the Ka2, but you've not been given the Kb2, remember you can calculate, the Kb2, from, the Kw divided by the Ka1. Because remember what we said, the Kw is equals to the Kb2 multiplied by the Ka1, the Ka1, which I already showed you, in the previous slide. So if you've been given the Ka1 and the Ka2, you can calculate, the Kb2 and the Kb1. Remember the Kw also is equals to the Kb1 multiplied by the Ka2. So if you know this, you can calculate, this one as well. Okay. So the key thing is the following. Take note of this. This is an amphiprotic species. So how do you determine the pH of an amphiprotic species? You derive an equation based on the charge balance, okay? And it can look fairly ugly, and I won't take you through all the derivations. In fact, I don't expect you to really know all these derivations, although you can take a look at it just for your understanding. But if you use a charge balance, manipulation, you end up with this equation, that the hydronium ion is equals to the root of the Ka1, the Ka2, the concentration of the amphiprotic species, plus the Ka1, the Kw, divided, by that ratio. So essentially, if I have an amphiprotic species, that is a diprotic, species, okay, then what I just need to do is invoke this equation to calculate the concentration of the hydronium ion. So it's as simple as that, okay? Meaning, in this case, I will just substitute this here. That's the concentration of the Hg. The Ka1 and the Ka2 are fairly known. All these are constant. And I can substitute them into that equation and get a pH, of 6.082. Remember the Ka1, Ka2, Kw, all of them are constants, that you'll be given. Take note of this, that you can even simplify this equation further, okay? If you have an amphiprotic species, it tends to be concentration independent, okay? Meaning I can cancel out, these concentrations, all right? And what I'm gonna be left with, is this relationship, that the pH is equals to the pKa1 plus the pKa2 divided by 2. Because if you look at this, the Ka1, Kw is very, very small, so I can neglect that. I can neglect that. I can neglect, that as well. And eventually, I'll be left with this relationship. The pKa1 is equals to, pH is equals to the pKa1 plus the pKa2, divided by 2. Okay? And so, essentially, you're going to see if I invoke this relationship and neglect, the Hg, you're going to see that I get a pH of 6.06, which is very similar to what I had here when I invoked or when I used the concentration. So essentially what I'm saying is a concentration, of amphiprotic species, doesn't contribute significantly to the concentration of the hydronium ion or to the pH, and so it can be neglected, okay? So if at all you have an amphiprotic species, that's the way you calculate, the pH. So the other last example is how do you calculate the concentration now of a completely conjugate base, So remember I had, the Hg as an amphiprotic species on the other side, on the other slide. The Ka2 gave me now the glycine, that doesn't have any hydrolyzable protein. And now this is, what you refer to as, a conjugate base. All right, so it's a conjugate base. So when you're dealing with a conjugate base, just like A, when we are dealing with a conjugate acid, we assume that it's a monoprotic acid, meaning the predominant reaction taking place is this. The glycine reacting with water, to give you, that's a KB1, to give you the Hg plus, the OH minus. And you can see the KB1 is very significant. All right, it's 10 to the power minus 5 compared to the KB2, which is 10 to the power minus 12. And so essentially you can neglect, the second, hydrolysis reaction, and imagine that most of the hydroxide is being generated, from the first hydrolysis reaction. And so based on that, of course, the K, I think I have it here in the next slide, the KB1 then is equals to the Hg, and the concentration of the hydroxide divided by, the G2 minus, and so forth. And so in that case, you've got the X squared divided by the formal concentration, which is a 0.05, minus X, is equals to the KB1, which is 5 times 10 to the power minus 5. And then you can solve for X. Again, you can make an assumption that 0.05 minus X is approximately the same as 0.05. And so that X can be neglected, meaning you don't have to solve the quadratic equation, meaning X is equals to the OH minus, and is equals to the root of, the KB1, which is that, multiplied by the 0.05, and you can solve, for X. And when you do that, you're going to see X is equals to that, and the negative log of that gives you the POH, which is that, and the pH is equals to 14, minus, the POH, and so you get 11.230. So again, take note of that. If at all you've got a diprotic base, which is what I have here, you assume is a monoprotic base, and that's the way you solve for pH. So you neglect the second dissociation, the second hydrolysis constant. So another example here is, assume I gave you an example as follows. You've got monohydrogen phthalate, KHP, and you've been asked to calculate the pH of 0.1 molar of KHP and compare it with 0.01 molar of KHP. The key thing is make sure you are able to recognize an amphiprotic species. You can see KHP is an amphiprotic species. So it's coming from the salt of phthalic acid. Phthalic acid looks like that. All right, that's phthalic acid. You can see is a diprotic acid. It dissociates, to give you, this one is removed, and so the Ka1, it gives you the phthalic acid, now the HP. Remember, this one is a H2P, and so this is the HP now, okay? And so what you're dealing with here is an amphiprotic species. And so because you're dealing with an amphiprotic species, you just need to remember the way to calculate, the hydronium ion for an amphiprotic species is to use this equation here. And if you want, you can also use this relationship, which is a close approximation of that, where the pH is just equals to, the average of the two pKa's, okay? And as you can see in my, maybe you can solve this, try to get the hydronium ion when you invoke those concentrations into my equation, and do the same for the 0.01, okay? And when you calculate both of them, please solve this at home, you're gonna see, the pH in any of these is very similar to just taking an average of the pKa1 and the pKa2. So again, for ambiprotic species, they tend to be concentration independent, and that's why we are neglecting, the concentrations in that case. Again, hopefully that's clear. Be able to recognize an ambiprotic species. Now remember, what we've done for the diprotic acids can be extended to triprotic acids, meaning you've got 3 hydrolyzable, proteins. A good example, as I said, is histidine, is an amino acid that its structure, the pKa1, is due to hydrolysis, is due to dissociation, of that carboxylic acid group. The second dissociation is because of the release of that proton due to that amide group, and the last dissociation is because of the release of that proton from that ammonium group right there. And you can see histidine is very related to histamine, which is most people tend to be quite allergic to histamine, present in fish and so on. Doesn't smell very good, sort of the rotting fish and so on produces a bit of histamine, and you can see they're very, very similar in terms of structure. But I hope you can see the pKa1, is 1.7, 6.02, and the third one, due to the release of that amine, is 9.08. Okay. And as I've done before, there's a triprotic acid system. There's a first hydrolysis, the second hydrolysis, and the third, hydrolysis. Similarly, it gives you, a completely conjugate base. This guy here, that's a first hydrolysis, and this is a second, hydrolysis, and finally that is a third hydrolysis. Okay, so you can see if you combine these two equations or these two reactions, you end up with this relationship. Okay, because you can see the H3A cancels out, this one cancels out, and so what you have is water giving you hydronium ion and the OH. Okay. On the other hand, if you combine these two relationships, you can see you end up, with this kind of relationship, because again, the H2A cancels out, this one cancels out, and so what you're gonna be left with is water giving you the hydronium ion and the hydroxide, and that way you've got the second relationship. And finally, if you pair these two relationships, these two reactions, you end up, cancelling out that. And again, what you have is water giving you hydronium ion and the OH. And that way you've got, this other relationship, right there. So if I have given you just the Ka's, you can certainly determine, the Kb's, because of this relationship. The Ka1 multiplied by the Kb3 is equals to the Kw, and so forth. Of course, the Kw is well known, is equals to 10 to the power minus 4, which I assume all of us, know that constant, what you call the autoprotolysis constant of water. So, as we had done before with the diprotic acids, if I give you, say, histidine concentration of 0.05 molar, and then I ask you, calculate, the pH of that solution, simply treat it, like a monoprotic acid. Hopefully that's clear. Treat it like a monoprotic acid, meaning that only one hydrolyzable proton is very effective. Okay. Alright, meaning the Ka1 is equals to x squared divided by the formal concentration minus x, and then you just solve x, and of course x is the hydronium ion concentration. If I give you the second or the first ambiprotic or intermediate species, take note of this relationship, that the hydronium ion is equals to the Ka1, Ka2, and so forth. And it's very similar, to saying pH is equals to the pKa1 plus pKa2 divided by 2. Like I said, they are concentration independent. On the other hand, if I give you the last intermediate species, take note of this. The concentration of the hydronium ion is a Ka2, Ka3, and that's a form of concentration and so forth, which again is very similar to saying pH is equals to the pKa 2 plus a pKa3 divided by 2, because again, amphiprotic species, they are generally concentration independent, and so the pH you get here is very similar to the pH that you get there. And then finally, if at all you've got a fully deprotonated histidine, now you need to treat it, as a monoprotic base, because in this case now I've got the A3 minus, meaning the only thing that's predominant is reacting with water, to give you, that's a KB1, giving you the HA2 minus plus the hydroxide. Okay, and so whatever that's KB1 is equals to x squared, divide by f minus x squared divided by f minus x, and the x in this case, remember guys, is the hydroxide, so you just need to calculate the POH. So again, if it's fully deprotonated base, treat it as a monoprotic acid to calculate the concentration of the POH. So I hope that's fairly clear, and I think I've talked about this. If at all H2 histidine is an amphiprotic species, the B, you just use this relationship. You just use that relationship. And you're gonna get the pH, if you use a concentration, the pH is equals to 4.01. But if you assumed concentration independence and just average the pKa1 and pKa2, you can see what you get is 3.86, which is very similar really to the pH of 4 that you got if you used the concentration. So you can see it's a close approximation. They are close enough. On the other hand, if you use a second amphiprotic species, remember this relationship, the Ka2, Ka3, and then the histidine and so forth, and you get a pH of 7.60. If you neglected the 0.2 and so forth, you're gonna find you can use this relationship, the pKa2 plus pKa3, and you get 7.55. You can see again they are very, very close. So if I were you, I wouldn't bother using the concentration. I would essentially use this relationship, just the average of the pKa's to give me the pH, because they are close enough. So one other application, of polyprotic acids, is the fact that, you can use them to make buffers or diprotic buffers. I'll give you a quick example, very, very similar to what we did before, when we were doing monoprotic acid buffers. So assume I've got a relationship like this. I've got oxalic acid, and oxalic acid, is a diprotic acid. And then I want to make a buffer, and I want to make a buffer of pH so you can see I want to make a buffer of pH 4.5 from taking oxalic acid and reacting it with hydroxide so that I can make its conjugate bases. Okay. So it's very important to determine which is the relevant equilibria, because remember there are two equilibria, because an oxalic acid, it can undergo the first hydrolysis to give you, the HA minus, and then it undergoes, hydrolysis further of this amphiprotic species, to give you that fully deprotonated base with a pKa2 of 4.3. So So the question is, which base pair, which acid base pair am I looking for to make a buffer, you know, of 4.50? Remember, the rule of thumb is the following. For a buffer to be effective, the pH that is of interest should be within plus minus 1 of the pKa. And so because I'm looking for 4.5 as a pH of the buffer, it means the most relevant equilibria, you know, would be the second one, because this pKa is within plus minus 1 of this pH, that pH. Meaning I need to titrate and add hydroxide to oxalic acid until the first equilibrium goes to completion, and then after that I protonate, you know, and titrate the second reaction halfway. And that's what I have here, you know. So determine the relevant equilibria based on this relationship, and ideally, you know, the desired pH, you know, should be very close to the pKa. And of course you can see the pH of interest is 4.5 and the pKa in this equilibria is 4.2, meaning this is the relationship that I'm looking for. So we need to fully react the first reaction, you know, and then after that, you know, react the second one halfway. So in this case, to react the first one, I need to add, I already know the oxalic acid, so I need to consume all the oxalic acid and convert it to the oxalate, okay? And, you know, I need to add the number of moles of the oxalic acid is 0.024. I need to add the same number of moles of the base, you know, so that I can consume all this, and that's what I do. And then I can determine the volume of the base, you know, that I added, you know, so that's the base that I added in the number of moles, and then I divide it by the concentration, and that gives me 50 mils of the base is what I needed to make this reaction go to completion. And then after that, you know, you need to react the second equilibrium expression by adding the base. So I starting with 0.024 that I formed. I add X number of moles of the OH, I don't know how much, so that I can convert it to the conjugate base. And then finally the equilibrium amounts would be, you know, what I started with minus X, what I consumed, or the base I added is consumed, and the conjugate base, you know, is what I formed, which is the X, and I can substitute it into my Henderson-Hasselbalch equation. The pH is known, is what I'm looking for, 4.5. The pKa2 is the equilibrium expression that is taking place, plus the log of the base, which is X divided, you know, by the number of moles of the acid, and I can calculate what the X is in terms of the number of moles of the base that I added divided by the concentration, and that gives me 20.44 mils. And of course I have to take that and add it to what I had used initially to react with my first equilibrium expression, meaning I need 70 mils, you know, of 0.5 molar concentration of the base, you know, to make a buffer, you know, of pH 4.5. And I hope it's fairly clear, you know, how we did that problem. So like you guys at home, you know, very similar to the problem I've just talked about, try to solve this problem. So you've got malic acid, again you can see it's a diprotic acid, and then you've been required to make a pH, a buffer of pH 5.2 from adding sodium hydroxide, reacting it with malic acid to make malate, you know, which is a conjugate base. So the question is, how much volume, you know, of this base do you need to add to malic acid to make that buffer? And again, it's very similar to the problem that I've just solved, you know. So solve that problem, and it's fairly important also for your midterm as well. So finally, when you're doing titrations, for diprotic acids, you're gonna see the titration curve is gonna have two inflection points, okay? So it's gonna look, like that, and like that, because it's got two inflection points. Because in this case, this is pH, and you're titrating it, with a base, okay? If you're titrating, a base, with an acid, you're titrating a base, with an acid, it's just gonna be the opposite like that, meaning I've got two inflection points because I've got two hydrolyzable protons. And I hope it's fairly clear. And that's all that I'm gonna talk about, with the acid base equilibria.